Hi, we are now in geometric sequence, and as previously, I will use GS to represent geometric sequence throughout the video. So in a geometric sequence, each term is found by multiplying the previous term by a constant. For example, we have, this is an ascending order of geometric sequence, 2, 4, 8, 16, and so on. And you can see here that each term is a multiply of 2 from the previous term. So generally, we can write a geometric sequence as A, AR squared, AR cubed, and so on, with A, its first term, and R, the common ratio, with R equals to Tn plus 1 over Tn. And n here is also a positive integer. The nth term of our GS is given by Tn equals to A dot R to power n minus 1. We also have two formulas for partial sums of GS with R less than 1 or R greater than 1 correspondingly. And in GS, we have sum to infinity with the formula A over 1 minus R. Now let us look at example 9. Find the general term, which is Tn, for the geometric sequence given. So we have an ascending order of GS here with A, the first term, equals to 8 and R equals to 16 over 8, which is 2. So general term here is Tn equals to A dot R to power n minus 1. And substituting our A and R we found previously, we have 8 times 2 to power n minus 1, and simplify it, we have Tn as 2 to power n plus 2. And we're done. For example 10, we have to find the ninth term of the GS for 27, 9, 3, and so on. So this is definitely a descending order. So we have here A is 27 and R is 1 over 3. As previously, we have to use the Tn formula, but this time we have to substitute in our n equals to 9. And with A and R, as we find here, to get 27 times 1 over 3 to power 9 minus 1, which is equal to 1 over 2, 4, 3. And we are done. For example 12, we are to find the sum of the geometric series 1, 1 over 2, 1 over 4, up to 1 over 2, 5, 6. The sum of a geometric series is Sn. So we can obviously see from this sequence, we have A equals to 1 and R equals to 1 over 2. They give us the final term, which is 1 over 2, 5, 6. But we do not know which n gives our final term. So here we write down our last term as Tn equals to 1 over 2, 5, 6. In order to find the sum of the first n term, we first need to find our n. So to do that, we have to use the Tn formula again with our A, 1 and R, 1 over 2, and equate it to 1 over 2, 5, 6. And finding the same base for both sides of the equation, we have 1 over 2 to power n minus 1 equals to 1 over 2 to power 8. And comparing the indices, we have n equals to 9. Now we know that the last term is 9. Then we can find the sum of the first 9 terms of this geometric series. And to do that, we have to use the formula for Sn for r less than 1 or less than 1, and substitute a, r, and n to get 511 over 256. And we're done. Now look at example 13. The sum of the first two terms of the geometric sequence is 36, and the product of the first and the third term is 9 times the second term. And we are to find the first 8 term, which is, in this case, S8. So as we can see here, there is no sequence given to us, so we do not know our A, and hence we cannot know our R. So we first let our sequence in general form, which is A, AR, AR squared, and so on. So taking out the information given to us, the sum of the first two terms is 36. So we have A plus AR equals to 36. And the second one, the product of the first and the third terms is 9 times the second term. So here we have A times AR squared equals to 9AR. Simplifying it, we have AR equals to 9. So we have second equation. So we have to solve these two equations simultaneously. And by using the method of substitution, we substitute 2 into 1 to get our A equals to 27 and R equals to 1 over 3. So after finding A and R, we can then find our S8 as the question asked. So to do this, we have to use the formula for R less than 1 and substitute our A 27, R 1 over 3, and N equals to A. And then calculating this formula, we will have S8 as 3280 over 81. And we are done. Hi, we now look at example 14. The first term of a GS is 27 and its common ratio is 4 over 3. We have to find the least number of the terms such that the sum of the sequence, which is Sn, exceeds 550. So now we can see that there is no sequence given, but we do have our A and R. And we have to find N such that Sn exceeds 550 or Sn greater than 550. So here, we have to use the formula for the partial sums of the GS for R greater than 1. So we have to substitute our A and R into Sn on the left side of the inequality to get the following. And simplifying the fraction on the left side of the inequality, we then have 81 times 4 over 3 to the power n minus 1 greater than 550. Dividing both sides by 81 and simplifying it some more, we then have 4 over 3 to the power n greater than 631 over 81. Since n is the index on the left-hand side of the inequality, we then have to apply log on both sides of the inequality, and dividing by log of 4 over 3, we now have the following. Then calculating the left-hand side and the right-hand side, we then get n greater than 7.136, and the least number of n such that n greater than 7.136 is then n equals to 8. And we're done. For example 15, we have to add up all the terms of the infinite GS as follows. This is what we call infinite because the sequence does not have any last term. So in this sequence, we have our A, 1 over 3, and our R, minus 1 over 3. To add up all the terms in this kind of GS, we then have to use the sum to infinity with the formula S infinity equals to A over 1 minus R. Substituting our A and R, we then have our S infinity as 1 over 4. And we are done. In example 16, we have to express this decimal in B as a single fraction. We have 5.459 with a bar on top of 5 and 9. So what does this mean? So 5.459 with the bar on top of 59 means 5.4595959 and so on. As we can see here, the 59 is repetitive except for 5.4. So we can write this decimal in the form of 5.4 plus 0.059 plus 0.00059 plus so on up till infinity. And notice here that the second term up to infinity forms a geometric series up to infinity, which what we call infinite geometric sequence. We now have our A as 0.059 and our R as 0.01 by dividing the second term with the first term. Then, putting 5.4 into a fraction and using the S to infinity formula, we then have these two partial fractions, and adding up these two fractions, we then have 1081 over 198 as a fraction for the decimal 5.4595959 and so on. And we are done. Now example 17, given that the sum of the first n terms of a series is Sn equals to 1 minus 1 over 3 to the power n, and we have to find the expression for the nth term, which is Tn. And hence, to find the first term and the sum when n goes to infinity. So note that also in this example, we are not given any geometric sequence, but we are given Sn. So we shall use the Sn to answer all the questions. So to find Tn, by using Sn given, we have a formula. Tn equals to Sn minus Sn minus 1. We already have our Sn, and now we have to find our Sn minus 1. To do so, we have to substitute our n minus 1 into our Sn as follows. So here is our Sn, and we have to minus with our Sn minus 1. So as you can see here, our n previously is substituted by n minus 1. Then we have to simplify our right-hand side of our Tn and simplify it some more to get Tn in a simplified form, which is 2 times 1 over 3 to the power n. Getting Tn means we can then find our first term, second term, up till terms that we want to find. But since the question asks for the first term, we then substitute our n with 1 to get our very first term, which is 2 over 3. Lastly, we have to find the sum when n goes to infinity. Looking back at our Sn here, we have 1 over 3 to power n. And as n goes to infinity, the fraction 1 over 3 to power n will go to 0. And then it gives us 1 minus 0 equals to 1 as our sum to infinity. Similarly, we can use our s to infinity formula to get our s infinity. And we're done.